So now we want to take the opposite example. What if we have the magnitude, okay, and the direction of a vector, but we don't have the components? How can we get the components from the magnitude and the vector? And the answer is we just do the same thing we've been doing all along. We use what we know about the right triangle. And this is a right triangle, right? So one thing we know about the right triangle is SOHCAHTOA. In other words, we know that the cosine of any angle, right, such as this angle, is simply equal to adjacent over hypotenuse, right? Okay, so I'm going to write that, adjacent over hypotenuse, right? But in this case, our adjacent is Vx, right? And our hypotenuse is just V, right? Which means that with a little algebra, just solving for Vx, we have that Vx equals the magnitude V of the vector times cosine of the angle, okay? This is how we get our x component always, okay? And if we look at the y component over here, we know that sine theta is equal to opposite over hypotenuse, right? And in this case, opposite is just Vy, so sine theta equals Vy over the hypotenuse, which is the magnitude of the vector, just V, right? And with a little math, we know that Vy is equal to the magnitude of the vector V times the sine of the direction theta, okay? And that'll always give us the y component, okay? So this is super simple. Once again, we're just using what we know about the right triangle to solve for the x component and the y component. This you'll have to do for the rest of your entire physics career. So much of physics is finding a vector and then being able to break up its x and y components, and we're going to show you why that's important in a second. Okay? So if you guys advance to the next slide, we have, it shows another coordinate system, but at a tilt. It says the components of a vector break up the same way even if the axis is tilted. Okay? And so this is just an important thing that I want to say, that even if we take this axis and we just rotate it, right? So it looks like this now. Okay? And now we have a vector v here. This is theta, right? In this case, even if we do this, the same rules apply, right? If now we just call that theta instead, we still know that the x component and the y components break up the same way. Vx will still be v cosine theta, if this is v, right? And vy will still be v sine theta, okay? Piece of cake, super easy. This is important because sometimes it makes sense to tilt the coordinate system, right? Like, let's say we're talking about, the famous example in physics, which I'll just use right now, is you have some kind of an inclined plane, right? And a box sitting on it, right? But since the plane is at an angle, it makes sense to call this the x direction and this the y direction, okay? So just know we can tilt the coordinate system and the same rules apply. In the next example that says, the slide that says muscles as vectors, we actually see why this works, okay? So here's what's going on here. We have a deltoid muscle applying a force on the humerus, okay? And so this is a classic thing, especially for you physical therapists out there, that you're going to have to explore. What is the effect that various muscles have on different bones in the body, okay? And in this case, we have, the humerus bone is kind of here off at an angle, so they actually have the x-axis being like this, and the y-axis being like this, right? And they're saying that the humerus bone, I'll just try to draw the bone here, is in line with this x-axis right here, right? But the important thing to know is that there is a force acting on that humerus muscle, F, and that force is 720 newtons, right? And so obviously, there's going to be an x component of that force pointing here in the x direction. That's Fx, right? There's going to be a y component of that force pointing up here in the y direction. Okay? Now, it doesn't matter if you put that here or here. It's the same thing. So if I want to just, here, call this fx, I can slide this over so it's easier for you to see the triangle. I'll call that fy. Okay? Does that make sense? So the question now is, how do we find the components of that 720 Newton force vector? And this is an important question because only one of those components is important for actually moving the bone up or down, right? Which one do you think it is? The y component, okay? Why? Why the y component? Okay, well, because it's the only one that's perpendicular to the bone. So the component that's actually pushing up or down on that bone is the only one that's has, you know, any kind of influence on it, right? And the x component of the muscle is just like kind of either pulling it or jamming it out of the socket, right? So it's not having the effect in terms of the motion, right? And so this is something that's important if you're a physical therapist to be able to analyze and understand where is the motion and where is the tension actually being applied on the bone, okay? So let's find those two components. Well, we remember from our last example that Fy, right, is just F, the magnitude, times sine theta, which in this case is 720 sine of, they have that force being, if you look on the slide, at 15 degrees, right? So it's sine of 15. And according to my notes, that is a 695.5 Newton force, okay? And our x component is F cosine theta, right, which is just 720 cosine of 15 degrees, and that is, according to my notes, 186.3 newtons, okay? And again, this is valuable because now we know it is only that 186.3 that is actually having any effect on moving the bone up and down, okay? It's kind of cool. We've isolated that. We've picked it apart. And this 695 is actually just like putting tension and pressure on the bone, on the socket, right? By just pulling or pushing, right? So something a physical therapist might want to think about is what are some exercises or ways of motion, right, such that we can lower this value and increase this value, okay? That's just something you might think about. All right, moving on. The next slide is just a recap of how to get the magnitude and direction from the components. So I'll move on from that. And then we have a misconception question. And the question is, the magnitude of a component of a vector must be less than or equal to the magnitude of the vector, equal to the magnitude of the vector, greater than or equal to the magnitude of the vector, or less than, equal to, or greater than the magnitude of the vector. And you guys are like, what? What is this? How do I find this? It's way easier than it looks. What are the components of a vector? Well, we just talked about it. The components are fx is equal to f cosine theta, and fy is equal to f sine of theta, right? These are the two components. And so you see that it's just the magnitude of the vector times a cosine or a sine function. And you guys know that cosine and sine functions only go from 0 to 1, right? So that means fx can only be between 0 and f, okay? Right? If cosine is 0, that's 0. If cosine is 90, that's f times 1. So the components can only be between 0 and the magnitude of the vector, right? In other words, less than or equal to the magnitude of the vector, which is the answer A. Okay? Does that make sense? Pause if you need to think about it for a second. If not, move on with me. The next slide has a summary of everything we've learned so far, how to get the magnitude and the direction from the components, and how to get the components from the magnitude and direction. Use that as a reference if you need to. And lastly, the last thing I want to say for this video is just a reminder that if there are 3 dimensions, okay, if the vector is pointing in 3 dimensions, you want to say that the vector is written as ax times I hat, or in the I direction, plus ay, or times j hat, which is in the j direction, plus a z k hat, which is in the z direction. K hat's in the z direction. Okay? Just a reminder of that. For the record, very few questions from this point on are going to be in 3 dimensions. We're going to get back to 3 dimensions a little bit more when we talk about torques. But for the near future, this is all you need to worry about. All right? Okay. In the next slide, in the next video, we're going to begin exploring how to add and subtract vectors, and I'll see you there.